Okay, let's start. So when we were discussing PSRR in the last class, and we saw that the definition of PSRR is essentially if you have a small signal excitation at the VDD, that is the PSRR plus, then in the open loop configuration, you figure out what is the incremental V out, that is V out by VDD, and divided by the differential gain, right? Divided by the open loop gain. Then I asked you to figure, then I asked the question that why do you always end up dividing it by the differential gain? And there was one answer, and then I essentially asked you to figure out under unity gain configuration, right? Under this feedback configuration, which is anyways one of the configurations that we will always use because you don't use any of these op-amps in open loop or difamps in open loop. So what do you think V naught over VDD will be? So did you work it out? So what will be V naught over VDD in this case? If you haven't, then work it out and tell me. You can follow the same principle. Okay. So I saw some of you were trying to find out directly V naught over VDD. Obviously, that is one way to go about doing it. But if you have an easier way of finding things out, why not use it, right? So normally, when you have any of these circuits, one of the ways to do obviously is figure out brute force V naught over whatever is V naught over the excitation. But other way is exactly the same thing that you did in last class. That is, find out short circuit current, find out output impedance, multiply, right? Normalize and multiply. What will be the short circuit current? How will you figure out short circuit current incrementally? First thing, short the output incrementally, right? So output gets shorted. And what will be the current through this short? We derived this current last class, right? What is that? What is ISC? So ISC is equal to, you can look at the last class's notes, right? Basically VDD by GDSN plus GDSP, isn't it? Sorry, VDD times. And how did we get that? Same old thing, right? So we figured out what is the looking in impedance here. What is the looking impedance at the drain of M1? 2RDS1, right? This is 2RDS1. So what is the looking in impedance from here at the source of M3? 1 over GM3 plus 2RDS1, which is approximately equal to 2RDS1. So what will be this current? This current will be VDD by 2RDS1. So this current will be VDD by 2RDS1. This current is flowing in, so it has to flow out. Okay. Similarly, this current is getting mirrored through the GM of M4, so this will come out. So the current due to this mirroring and this, if you add it up, it will become VDD by RDS1. But on the other hand, you also have this here, right? So that will contribute to another VDD times GDSP. So you add them up, you get ISC to be VDD times GDSN plus GDSP. Okay, so This is nothing new. This is exactly the same thing we did last class. Now the difference is ISC isn't changing because when you are shorting the output, the configuration between the input and the output is exact. I mean, the configuration between the case where you have feedback and you don't have feedback are essentially identical, right? But the difference is the output impedance, right? R out was under open circuit condition, the R out was GDS N plus GDS P 1 over, right? 1 over GDS N plus GDS P. But in this case, what will be your R out? What will be the R out here? Let me sketch it again. Talking about incremental, we can get rid of the current sources and all. So this is also grounded. What will be the R out here? Yes, Pratik? Yeah. So same thing, right? You can think of it in multiple ways. Same old, V test, apply V test and figure out I test. So if you apply V test here, what will be the incremental current? What will be the incremental current through M2? No, right? Is source of M2 rounded? Then what will be? What will be this current? By now you should be by hearting it. I think I personally have done it like 5 times in class. No, how does it matter whether it's diode connected or not? I mean, does it matter? Because I am forcing the M2 with a voltage source. Exactly, right? So this current will be V test into GMN by 2 or GM1 by 2. So this current flows out, correct? This current is flowing out and going into this mirror, gets copied here also. So what is the current that is coming out of V test? So this will be V test times GMN, right? So what will be the R out? One over GMN. Okay, so you can do it in another way, which is the symbolic way. So what was the symbol of this that we replaced it with, this difamp? Okay, tell me what are the approximations? What did I neglect?
GDS of M1.
GDS of M1, fine. So is that a good enough approximation? So that's good enough approximation. What else?
Then for M3 it's a direct connected.
Right.
1 by GM.
Fine.
Then for this one, but the current is going, so same current will.
Correct. So I also neglected the GDS of M4 But is that a good enough approximation? So if I didn't neglect the GDS of M4, what would have been the current through that GDS of M4?
There will be slight variation because of
Yeah, but what will be that current? What will be this current?
VTest
times GDSP. So I am neglecting VTest times GDSP with respect to VTest times GMN. Right? So good enough approximation? Fine. So other way of looking at the same thing is, if we go back to the previous lecture, we saw that this differential amplifier is essentially, we are replacing it with this. And it has an output resistance of 1 over, let me just write in terms of conductance. So this is GDSN plus GSP. And this diode connection of M2, that is the input to output, is essentially a representation of this. The positive terminal is incrementally grounded, and I'm trying to figure out what is R out. Okay, so if I try to figure out what is R out, then what do? I apply a V test there, and then try to see what is the test current that I'm drawing. So if this is V test, so you have a current here that is V test times GDSN plus GDSP, but the more dominant contribution will come because this V test is appearing here. So it is exciting that GM, which means this current will be how much? This is GMN times V test. So the total current that you are drawing in is GMN plus GDSN plus GDSP times V test. So essentially your R out is is 1 by GDSN plus GDSP plus GMN, so approximately 1 over GMN. Okay, fine. So if this is the case, what is V0 over VDD? You know ISC, you know R out. So what is V0 over VDD?
So this GDSN plus GDSP,
Yeah.
this conductance was a case when there is no feedback. Right?
Yeah, that's the output conduct.
But now we are closing the loop, and then we have to find this according to the both the.
Yeah, I mean effect of output impedance when you close the loop, right? So again, I mean, one of the assignments you did, right, finding out when the loop is broken, impedance, output impedance is when the loop is broken and when the loop is closed. So what was the conclusion? When the loop is closed, you have low impedance. Again, that makes sense because when negative feedback is working properly, you are not supposed to have any high impedance node. Okay. So, so what is V0 over VDD now? ISC times R out. What is that? Yeah, which is approximately, what is ISC? Why is IS in ISC? How come you are getting GMN?
Sorry, GDS.
Yeah, right. So you essentially get GDSP plus GDSN by GMN. This is equal to how much? This is basically 1 over the differential gain, right? Or the gain of the amplifier. Okay. So essentially this is the definition of PSRR is V naught over VDD under open circuit condition divided by the gain. Right. So that's the definition of PSRR, the standard definition of PSRR. And the reason that is an acceptable standard definition is because you don't ever use your circuits in open loop, you use it in closed loop. When you put it in closed loop, your all the bad things, right? All the bad things that is supposed to happen goes down by the factor of the gain, factor of the loop gain, right? So if I draw if I again go back to at the very beginning. So we had, let's say we had a loop gain of L of S. And we close the loop here. And if you remember, we modeled some injections. This injection can be anywhere in the loop. We modeled it here. And I asked you to figure out what will be the effect of, if this is, let's say, Vn. So what will be the effect of Vn on V out if the loop gain is very high, or whatever will be the loop gain, right? And what did you find? It used to reduce by the factor of the loop gain, right? Any error is because ultimately what is sacrosanct? The sacrosanct part of this entire loop is it's trying to keep the virtual ground, because if you have high gain, if L of S is infinity, if it has infinite loop gain, V of n should not have any effect. So L of S becoming infinity is equivalent to saying AV is infinity in a differential amplifier or in any amplifier. Okay, so that's essentially the reasoning as to why we divide almost everything by almost all parameters in all the DC parameters, at least in op amps. You have CMRR, even you can do it for CMRR, you have PSRR and everything. So those things are always normalized with respect to the open loop gain, not because it's like mathematically convenient, but because moment you put it in negative feedback, whatever bad excursions that are supposed to happen goes down by a factor of the loop gain. So it makes sense to define these parameters with respect to loop gain. And it also gives you a design handle. As a designer, let's say you are given a spec that this power supply rejection ratio has to be minus 100 dB. Okay. And then you did your design and you figured that it's probably minus 90 dB. Then what do? Instead, intuitively, you should immediately come to the conclusion that I cannot do anything with the excursion at the VDD. That is coming from somewhere. All I can do is maybe increase the loop gain by 10 dB. Right? So if I increase the loop gain by 10 dB, automatically my circuit PSRR will increase or will become better. Okay. Okay. Any questions? Okay, so this was as far as the PSRR plus, right? So similarly, the moment you have plus, there is a minus. And what is the minus is essentially plus was how the circuit was reacting to the changes in VDD. Minus is how the circuit is reacting to the changes in ground. So let me take the thing. So let's say this is VP. So I till now I was considering ideal current source at M naught. So if I had considered ideal current source at M naught, what would have been the effect of excursions in VG and D? Nothing, right? Ideal current source, no current would have changed, nothing would have happened. So that is not a good enough model, right? Because you never have an ideal current source. So we have to use a realistic current source with all the realistic non-idealities for M naught. Okay, so this will be GDS 0. Pardon? Okay. So so now you will have to approach this again in the similar way of figuring. I mean, you find out under open loop condition what will be V naught over VG and D, and then divide it by the gain of the difamp. Okay. So for this again, I mean, you will have to consider the GDSP, and you will also have to consider these, right? Okay, so again, go by the same way, figure out what is short circuit current, and then you can multiply it with the output. Right. Correct, right? Yes. Correct, exactly, right? So yeah, that makes sense because you have her question is in the previous case here, your R out is changing, which means gain is also changing, right? Obviously, gain is changing because this is under what configuration? This is essentially a unity gain feedback, kind of a buffer, right? And the whole purpose of what we are doing is essentially to make a good buffer because it's supposed to be driving any load. The load changes, the output shouldn't change. So that's what we are essentially making. It has a gain of 1, but the crucial thing is that it has a gain of stable 1. It doesn't change if something else changes in the circuit. And that's the whole purpose of doing negative feedback. Okay, so I will give it as a homework or do it yourself. I will not derive it in class. We will discuss it in the next class, right? So figure out what is PSRR minus. So this is PSRR minus V0 over VG and D divided by again. Okay. So this is do it yourself. So the other thing that I wanted to discuss was when we were at the end of the last class, there was this question that we simply assumed that when we put this difamp in negative feedback, it was getting biased. Okay, any questions? I heard somebody sense. Any questions, anybody? Okay. Okay, so there was this, it's actually a good question that, I mean, we didn't talk about the fact that what happened, I mean, we simply connected the drain and the gate of M2, and I didn't talk about whether things are getting biased properly. I assume that things are getting biased. So is it a fair enough assumption, or if it's, I mean, how would you argue if somebody comes to you and say that it's not getting biased? Prove it to me, whether it's getting biased or not.
So if you can ensure that the left arm is biased,
Yeah.
in that case the same current will flow in the right arm because of this M3 and M4.
Okay. So how will you go about arguing that?
Because the VSG of M3 and M4 are same.
VSG of M3 and M4 are same. Okay.
So if you can ensure that the M3 is M1 is biased properly, then same current will flow to the M2, and M2 is already biased because it's
Correct.
connected.
Okay. But is it possible that I mean M2 is off? I mean all the current flows through M1. It's possible, right? In principle. This is what you have. This is all you have. Everything is. I mean, there is no hiding anything. So there is no ifs and buts here. Whether this is going to get biased or not. Yes. Huh. Yeah. Tell me, what is allowed? I mean, there is the rules of transistor are same, right? Not driven by legal jurisdictions. Okay, fine. So, okay. So his argument is, let's assume M2 is off. If M2 is off, which means what happens to this gate voltage? It has to need not be less than VDD, but it's definitely not closer to VDD. It will be lower. If it's lower, then can you comment on the state of M3 and M3 is in saturation? What about M4? So let's assume this goes to 0. This goes to 0 volts, right? Extreme case, right? For the purpose of argument, this goes to 0 volts. Then what will be the state of operation of M4? It will be in saturation. And M3 and M4 are current mirrors, right? So if I assume all the current has flown into M3, which means this is I0, this is I0. But where will this I0 flow from that is coming through M4? M2 is off, right? So this condition is not valid. Okay.
Why are you assuming that it's 0?
No. I mean, I'm not assuming. You can start off with any condition. So it's basically argument of contradiction. So you start off with an assumption and try to prove that assumption is wrong. Okay. So the other way of argument is, which is probably, I mean, which will help make another point, is the fact that let's assume that, I mean, 0 and completely one-sided shift is probably an extreme condition. Let's assume that slightly higher current is flowing through M1 than M2, right? You can go either way, but let's assume that. So if that is the case, if more current is flowing through M1 than M2, then what is happening? Okay, so the easier thing to do is so whenever you are stuck with these conditions, when you don't know how to start and you are trying to figure out exactly what's going to happen, neglect all the non-idealities and then proceed, and then see whether you are getting stuck somewhere. If I'm getting stuck, I can come back and renegotiate my assumptions. But you can start off by assuming that there is no GDS. If there is no GDS, okay, if there is no GDS, and let's assume that this is, instead of I0 by 2, is I0 by 2 plus delta I. Okay. And this is I0 by 2 minus delta I. Because total has to be I0, right? So if that is the case, what do you expect this voltage to be? Initially, let's assume that if everything is I0, this is supposed to be some Vx, capital X. But if there is a slight shift of current in one side, what do you expect this voltage to be? It will be some non-zero. And why should it be non-zero? How will you argue whether there will be an incremental change in Vx? I have the incremental current, right? I can argue from that respect.
So that node seeing the same impedance and current is increasing. So voltage should be
Is the current increasing?
because this side is delta I is coming to that side.
Yeah, fine. So,
So at that point, this delta 2 I 2 delta I will be pumping the charges of that node.
okay, but okay, which side is 2 delta is flowing? Where is 2 delta? Okay, I naught is same. Okay, but who is setting Vx? Then you have to see, right? Right? I naught being same doesn't necessarily mean that Vx will be same all the time, isn't it? I can have a different condition. We saw some conditions, isn't it? Earlier.
Left side is I naught by 2 plus delta current is increasing. Vb is fixed. So that Vx would change.
Okay, so why? That's the question, right? See, I can also argue in this way. I can argue using superposition. I can say that let's take this delta I at a time. So if I only figure out if I find out what is the current, incremental current that is coming through this, okay, and what is the impedance that I am seeing looking up, right? So if I am seeing 1 by GM2, what will be the voltage excursion at Vx?
The current times that.
Yeah, so delta I times 1 over Gm. And now I go consider the other minus delta I. And they are in opposite direction. So it will not move. So it will not move. Vx will not move. So fine. So if Vx is not moving and you are assuming delta I to have moved, then what is the conclusion? No, so what I mean, can I conclude something on this on the voltage at the gate of M2?
The source is not changing, so it should not change. So the same current.
No, we started off with the assumption that there is a differential delta I. Source is not changing, so gate has to reduce. Gate has to go down, not up. Right, it has to go down. The current through M2 was initially I naught by 2. Now it has reduced from I naught by 2. So the gate has to go down. So if gate goes down, yes. Why? Okay, yeah. So I'm coming to that contradiction. Right. So therein lies a contradiction, right? So the argument is, as he said, that there is a current mirror here. This will be I naught by 2 plus delta I. Right? So you cannot have a case where you have through the top you are having I naught by 2 plus delta I and you have I naught by 2 minus delta I. When you neglect GDS, if you have GDS, then you can say something else flowing into the GDS. Okay, so this condition is not valid.
So what is the impedance flowing at the source of input?
Okay, that's a good question. If you look, ideally that will be infinity, right? Yeah, but that's not particularly true because when you are making this assumption, you'll have to also take into account the fact that there will be there is a current mirroring effect through M3, M4 also, because this current that is coming out, this plus delta I that is coming out, that is also coming out through M3, right? So you are correct what you said, that if I only look into, if I just take this into account, if I just take this into account and look into the source of M2, I should get infinite impedance because I have neglected GDS, right? So then the following argument can be in the limit it's not. I can put the GDS back and then make that argument.
The value will be really high because for the M2
No. So the value will not be high because you have another mirror through M3. You understand? So see, this current that is coming out through here is also getting mirrored, right? So because of that, you will not get only GDS effect. There is inherent feedback because of the mirror. Okay.
Then what is the impedance looking at the drain of M4?
In this configuration, if you only look at the drain of M4, so how will you figure out the impedance? If you look at the drain of M4, you'll have to put in a source and then look up. In that case, it's infinity because there is no mirroring effect there. Okay, but the critical point is that if you, when you only look up, when you apply a source here and look up, then you are essentially saying I am not taking into account the mirroring effect that can happen because something can flow in this direction and take action through M4 also. Right? So M4 in isolation is giving you infinite, but there is another path that is can excite the gate of M4. So that can introduce another current because of this mirror. Right? So that's why simply looking up you will not get infinite impedance. So in isolation, M4 is giving you infinite impedance, but when you are making that assumption, are you making that you are inherently making the assumption that the gate of M4 is not getting excited. It's incrementally rounded, but that's not always the case. But what you asked is a very good question that I kind of facetiously made an argument that looking into M2 is 1 over Gm, but that's not always true. But I mean, what other way of looking at it is you can make the same argument without neglecting GDS.
So sir, whenever we are applying the stage voltage here,
Yeah.
at the gate of M2 or gate and drain are shorted, so that voltage is creating some current that is influencing M3, and M3 is influencing M4.
Correct.
And because of that, this should not be infinite.
Correct. Yeah.
Resistance.
Yeah. See, another way of, I mean, okay. So if you are not convinced with what I said, right, and you want a simpler way of looking at things, this should convince you. So essentially, this is what we are doing. Okay. So if you assume this V out is higher than, assume V out is lower than VB. If V out is lower than VB, what will happen? You'll push in current and it will pull it high. And if V out is lower than VB, it will pull in current and push it back. So you have inherent negative feedback. And because of that, the only possible solution under infinite gain condition is VB equal to V0. Right? So this is this is the simplest way of looking at things, but I mean, now since you are doing a full-fledged circuit course, I would have also want you to understand it from the transistor level.
And also you can consider the GDSP.
Yes. So if you have GDSP and GDSN, what will be the effect? If you have R out, what will be the effect? Will VB be exactly equal to V0? No,
some current will flow.
right, and this will not be exactly equal to V0, and the difference is essentially the steady state error on over loop gain, right? Okay, fine. Anything else?
So the source of M2 is if at all is 1 by Gm, then we are inherently assuming that the gain of the M2 is incrementally down. Right? Yeah.
Okay, we are assuming that there is the load at the drain of the M2 is not high.
If at all the top of the M2 current source is there,
Right.
then definitely we will.
Yeah. Yeah, true.
But the circuit is present, so how can we assume that this load is incremental?
So what I'm saying, you don't have to argue, right? So if that argument, if you're not comfortable with the argument, so this entire thing is coming because we have neglected GDS, right? So it basically becomes a fight between two infinites. So if that you're not comfortable with that, what you can do is you can put back GDS and then argue.
So now it is corrected by.
Yeah. Right. So you can even connect the GDS here and then argue. So same argument can be made. Another interesting argument that can be made is that don't put it in negative feedback, and you assume that both M2 and M1 are connected with identical bias voltages, and then argue what will happen to the drain of basically the output. Okay? Will it be higher than the left arm or the lower than the left arm? So that argument can also be made. Okay, fine. Any other questions? See, by now you must be, I mean, you should be tired of me getting, I mean, putting in the same circuits in open loop, closed loop, and trying to make the same point. And I want you to be tired of this, because this should be second nature. Okay, so you should be able to look at it and say that, okay, I know this. Don't hammer it anymore. But I'm not getting that vibe from the class. That's why I am boarding you.
Open loop condition of setting all the transistor in proper operating point.
Pardon?
In the open loop condition, let's open as
Yeah.
and setting all the operating point exactly with the
Okay.
and making the closed loop condition.
Yeah.
So that operating point reflects that.
So the open loop operating point and the closed loop operating point need not be same.
Doing that, again I have to.
So that's why you don't start off with open loop operating points. You put it in negative feedback and you put some high impedance, and then you try to break the loop while keeping the operating points same, right? So otherwise you are doing two different designs. Yeah, I'll come to that. So he raised a very, I mean, thanks for raising that question. So I was planning to address it at maybe the next class, but since I have posted the project, let me mention that also. So have you got a chance to look into the project? Okay, so it's essentially a differential amplifier. You'll have to design this. So his question is, I mean, should I design the difamp in an open loop and then close the loop and then hope for the best, or is there a better way of approaching it? So there is indeed a better way of approaching it, and that is that boils down to this, right? So again, let me sketch this L of S thing. So this your V0 and Vi, they come with some DC quiescent, right? Now the question is, how do I set the VDC? DC out, let me call it. So if I close the loop, will VDC change? It can change. Okay. But then how do I design this L of S? The L of S in this case is your difamp. How do I design this L of S if I don't know what is going to be my VDC out when I close the loop, right? So the way out from that is the fact that what you are trying to get at here, you are trying to figure out what is the, you are trying to find out the transfer function between L of S, between the input and the output nodes of L of S, that is V0 and VE. VE and V0. So V0 over VE is your gain. So you are trying to maximize that gain, but you can only get a gain from an active device if it is biased properly. So you have to bias it. You have to assume that it has been biased properly and then proceed. So it's one thing assuming that in a pen and paper. It's another thing when you are handling real circuits, right? So what is the main issue here? The main issue is I want V0 over VE to be high across frequencies, because my input will not be particularly DC. My input will change, but the DC condition needs to be set by feedback also. So I can decouple these two. And what am I essentially saying? What I'm saying is that at DC, right? At DC, we don't have any signal. That's the inherent assumption. Let's assume that at DC, no signal, only bias. Okay. And at non-DC, omega naught, we have signal. So this is similar to when you bias your common source amplifier with a capacitor, decoupling, and all those things, right? You assume that at signal frequencies, the capacitance is shorted. At DC frequencies, you are only setting the bias. Same argument. So now this bias we are trying to, so now if we want to decouple this, you already know one way, that is you already knew the way of how do you bias a common source amplifier with a capacitor, resistor, divider, and all, right? So if we have to do that here, what would you like to do? You would like to break the loop at non-DC because you want to figure out what is the open circuit gain, right? You want to break the loop at non-DC, but you want to keep the loop at DC because the DC is supposed to set the loop is supposed to set the VDC of the output. So what is the strategy? Given that let's say you know how to bias those common source amplifier with capacitance and resistances. So what will be the strategy? So do one at a time. Let's assume that I want to break the loop at high frequencies because I want to know what is V0 over Vi at high frequencies. Open loop V0 over Vi. So I can simply break it here. Right? If I break it here, then V0 over Vi is L of S at high frequencies. So how do you break anything at high frequencies? Putting something. You put an inductor, right? So let's put an inductor. So in your simulation, you can put an inductor of very large value, right? Whatever is a large, maybe 1 kilohenry or something. So essentially say L infinity. Okay. So if you put this to be L infinity, then what happens at DC? It is shorted. So your negative feedback is established in DC. But your V0 over Vi, whatever value you will get at non-DC frequencies will be equivalent to L of S. Right? So this essentially is the principle. Now, how will you do it using your difamp? Okay, so what is the feedback? Where is the feedback getting set? Your feedback is getting set through the drain of M2. So I can break it here. Right? So this is L infinity. And whatever is, if I call this one to be V0, so whatever is V0 over Vi will be your open loop gain. Correct? This is under unity gain feedback. Okay. So now, so in certain cases, you will probably not be able to apply this also directly. So in that case, if you have to set this voltage, set this DC voltage through something else, right? Let's assume. Okay, so let's not get into that. What I am trying to say is that now you might want to figure out what the loop gain is by applying I mean, this is a particular case where the loop gain, you will be able to get whatever loop gain you want. I mean, you will be able to simulate whatever loop gain you want. But let's say you are under a condition of, I think I gave the non-inverting configuration in the project, right? So let's say you have an inverting configuration, right? So let's say you have this condition. You have let's assume you have this condition. And then I ask you to find out the loop gain. So again, you will have to break the loop. But where is the loop getting set? Loop is getting set through this. So you have to break the loop somewhere. So again, in our analysis, we have been breaking the loop here, because that seems to be the most convenient place to break. We can still break it there, but how do I break it there while ensuring that the DC operating point is not getting compromised? I can put this L infinity here. Okay, so under AC condition, there is no path through negative feedback, but at DC, your condition is set. But then how do you figure out what is your loop gain? Because in our case, we were applying an input here, V test, and we were observing the voltage here, V return, and while shorting this, obviously. So you'll have to apply a V test. How do I apply a V test without disturbing the operating condition? This V test has to be incremental, right? So you have a small incremental AC source in your simulator. So you'll have to apply that V test there and observe V return. Observation is easy, but how do you figure out what is, you have this AC source, which is V test. I have to apply this V test here without disturbing the operating point or the DC operating point. How can I do that? Through a capacitor, right? So I can simply add another capacitor, C infinity. In simulator, you can put anything, doesn't really matter, any large value. And then you figure out what is V return by V test, and that will be a loop gain. Okay, so these are few of the standard practices that we follow to figure out what the loop gain is, while not disturbing the operating point under DC condition. So here the feedback is setting the DC, and then you optimize your circuit. Then first time you will be, it might so happen that first time you put everything in feedback, things don't work out. Maybe some transistor in saturation, some in linear, some in cutoff. Then you go back and try to debug the circuit with the feedback in place. Don't make it an open loop connection and debug, because your circuit ultimately will get put in a feedback mode. If you remove the feedback and debug, you are essentially designing, you are doubling your effort, because you are first optimizing it for open loop, then you are optimizing it for closed loop. There's no point. You can basically optimize that, put everything in negative feedback and start optimizing them. And the breaking part of the loop can be done by these L infinity, C infinity things. Okay, and LT spice in fact gives you another way of breaking. There is an element in LT spice which you put inside the loop. It will do the job of breaking and figuring out loop gain. I'll send another email informing about this. Yes. You tell me, how will you figure out? Yeah, exactly, right. You have to figure out the impedance and then see, in the regions of operations, in the operating frequency ranges, this L infinity and C infinity are not getting shorted essentially. I think LT spice will give you whatever value you want, right? But don't go into like terafarads and gigahenries, right? So then the simulator sometimes doesn't converge, because ultimately it's a numerical simulator. It wants some values in a range. Okay, what is the purpose of C infinity? You would want this voltage to be V test, right? So once you know what is L infinity, then you know what is C infinity. Then it's the ratio of voltage divider, right? Then between L infinity and C infinity. Yeah, but if L infinity is very high, then the resistors don't come into picture, right?
Question like, in a differential amplifier or any, if I consider simple MOSFET, okay, if I bias it in the source terminal with the current source, and if I make the gate floating, so what will happen?
Coming in?
If I bias the transistor, common source amplifier,
Okay.
by a current source.
The common source amplifier you have applied what? This is a common source amplifier, and you applied a current source here. Okay.
Then if I make a gate floating.
Okay. Yeah. What will happen? Tell me.
The gate terminal.
What will happen? You tell me.
So we get a voltage corresponding to.
Yeah. So now, okay. So let me throw it open to the class. So the question what he is asking is, I take a transistor, ground the source, apply a current source here. What will happen to the gate? Will the gate biased to some voltage? What will happen? The question is, I mean, whatever you are seeing, this is the circuit. Nothing additional. Okay, so this is the circuit VDD, and gate is open. So what will be the gate voltage?
Mathematically, the gate voltage will be there, but in practice, because reverse information is not possible.
So why do you say mathematically the gate voltage will be there?
If I put the VG ideal equations
Which equation will you put?
in
Why? What makes you put that saturation region equation?
because current source is present.
So, yeah, current source is present. So,
That current to satisfy that current, VG somehow it should be set.
why? There is no connection between output and VG, right? So how will it get set? Pardon? Yeah, right. So, okay. I mean, one might say that, I mean, since there is no VG, the current in I0 has no, I mean, you don't have any business in saying that the VG has been set to the current appropriate to I0. The VG can be anything. I mean, maybe it had some voltage which got coupled when you started the circuit. It can as well be zero. Doesn't really matter. Right? So what will essentially happen is that this voltage will keep on increasing because you are pumping current I0 into an open circuit. Okay, and if your I0, I mean, if now it depends on how good your I0 is. Right? So if whatever voltage it can sustain across it, it will sustain. After that, it will break down. Yeah, there's nothing. Right? It's an open circuit. So okay, so let me give you another. Kind of another way of thinking about it is, let's assume that you put this I0 and you have this VG. You automatically have this VG, right? What are you assuming? Pardon? Yeah, but how are you, I mean, how will you get that VG? You're assuming there is some way that information at the output is being fed to that information of that I0 current is going out, I am trying to sync, has to be sent. Right? VG is I mean, how will the gate know what is happening at the drain? Yeah, you are assuming feedback. Inherently, you are assuming feedback. And if there is no feedback, it's not going to happen. I mean, this force doesn't exist. If, I mean, this VG is getting set, had gotten set automatically.
In the lab, in discrete circuit, to put this will come to, I think it will burn out.
Yeah, something will happen. Your I0 will turn off, or if you have this fixed current sources, you will see ping.
So sir, no current will flow through the transistor, right?
Yeah, you tell me now. You ask the question.
So this I0 current will charge up the capacitor.
Yeah. And eventually, maybe the transistor will break down or something. Okay, so then you have to assume second order effects, right? So what you have here, you essentially have a PN junction diode here, right? You have multiple PN junction diodes here. Correct? You have one, then you have, if I there is this junction and there's a channel, right? And channel is not existing because you don't have VG, right? So maybe the first thing that will happen is this voltage will go up, and this voltage will go up, and the reverse bias current through the diode will start increasing, and the diode will eventually break. And that's what might happen, right? So this current might go through that. But if the reverse diode voltage that is required to break down that diode is very high, then before that, maybe I0 will shut off. So it now depends on which second order action dominates. Okay, so yeah. No, right? So how will you? So you will never reach that DC operating condition, right? So maybe if I put this, it will make the point clear. So you have capacitance here, right? Maybe this is CdB. So when you turn on your current source, it will take some time for the circuit to saturate, right? So when you turn on everything, what is tending to happen? This CdB is this voltage across this capacitance is increasing. The current is still flowing, but current is still flowing into the capacitor. And you might say that capacitor is the intrinsic part of the transistor. Then yes, when I say the transistor is not shut off, what I mean is that through the channel between drain and source, there is no current. But if you let's say put an ammeter at just around the drain of the transistor and are trying to figure out, you will get some reading. But that current is not flowing into the channel. That current is either flowing into the reverse bias diode or it's flowing into the CdB, and those things that we haven't considered till now. Okay. Okay. So, I mean, this time I didn't, but I normally start my course with this question. Normally, I start my course with this question, that if I put it like this, will it get biased? And then we come into the fact that if it doesn't, then if drain increases, you have to telephone the gate, right? Okay, fine. So essentially, we till now we have been dealing with differential pair, but differential pair, whatever we have seen, is essentially another fancy way of making another common source amplifier. So the issues with common source amplifier still persist. That is, you might not have enough gain. If you don't have enough gain, what do? You put cascode, right? So the same thing happens here. So if you don't have enough gain, you will have to do something about it. And cascoding increases the output impedance and can give us more gain. So the issue is the output impedance is essentially a parallel combination. Looks like a parallel combination of M1, M2, M4, right? So the output impedance looking here, is equivalent to saying that I am looking into the output impedances of M4 and M2, GDS4 plus GDS2. So if I have to increase the output impedance, I have to put something here. I have to put something here which increases the output impedance, right? So we can put. So now you tell me, how should I go about putting things? To put a cascode, right? I can start with the PMOS side. So, and I can then put another in the NMOS side. Then you have to, then you have to bias these also. You cannot just leave it floating, right? So how do I bias, let's say how do I get this voltage? Let me call it M6. Yeah, so how do I, so essentially the question is, what should I do? How do I bias this? Let me call it VCAS P. I can do another direct connected MOSFET because I know I have current of I0/2 flowing. So this essentially is a mirror. This is a current mirror, right? And we have spent 1 or 2 classes on designing current mirrors. So you can choose, take your pick, whatever you want. So, I mean, the one that we did in the quiz, the wide swing current mirror might be a better thing to do because you don't compromise on swing. So how do I put this wide swing current mirror? I draw it a bit neatly. And this voltage here is essentially okay. And I can put another here, and then I have to figure out what this voltage is, Vcas. Okay, so we'll see how to figure out what is Vcas. But if I do this, even without doing any analysis, let's assume things are getting biased properly. What will be the output impedance now? So earlier it was GDS4 plus GDS2, but now I have Cascode. So what will be the out?
What is sum of all the GDS of?
Is it only that? I didn't understand. So what is, I mean, okay, so think of it in this way. What is the, effectively, if you have this, if you didn't have this, it appeared as if you have this configuration, right? The output impedance seemed like the output impedance of this. Right, so this was 1 over GDSN plus GDSP. Now you have inserted cascodes. If you insert cascode, what will be the output impedance?
Intrinsic gain of M6 and M8.
Correct, right? So it will essentially go up by a factor of the intrinsic gain of M6 and M8, right? So if this R out was, this R out will be this R out without cascode times, or let me not complicate it like this. So yes, R out will be essentially be so the looking in impedance up was RDS4 initially. So now it would be still RDS4, but multiplied by the gain, intrinsic gain of M6, that is GM6 times RDS6, in parallel with looking in impedance down, right, which was RDS2 multiplied by GM8 times RDS8. Okay, so it's effectively, I mean, what I did was, if you had this condition, incrementally, I am moving from here to here, right? So this is M2, M4. So I'm moving from this R out to this R out. because the circuit on the left had an R out of RDS2 parallel RDS4. The circuit on the right, being a cascode, will have more R out by the gain of increased by the gain of the cascode transistors. But note that this is only a model, right? Because it's not as if the output impedance is of your difamp is a parallel combination of M4 to M2. It's not because those are the only two transistors. There is current mirroring action happening and all those things that are happening, that is making it behave ultimately like this configuration, like this configuration. Okay, so I can do the same analysis again, but since I know what's going to happen eventually, I can as well take the leap. Okay. So again, it's good practice to do it once yourself. Do it once yourself and then satisfy yourself, right? So basically, you exactly the same procedure as we used to find the output impedance of difamp, just with two sets of transistors extra in place. Okay, so that also give you some practice.
So
yes.
In that current mirroring action that was affecting that resistance.
Yeah.
Will there be any effect in that?
Tell me, will there be or not? There is still a current mirroring action, right? Yeah, so it will have, right?
So is that equation?
Yeah, do it yourself. Do it yourself. Let's talk in the next class. Okay. By the way, okay, so this is the output impedance. What is the effective short circuit current or effective transconductance? Will that change between the cases where we put the cascode and not put the cascode? No, right? It's, as you said, it's decided by M1, M2, right, which hasn't changed. So your effective effective transconductance is still GM of M1, just that the output conductance has decreased. Okay, that's how you get more gain, right? You push in current into a high impedance node. Okay, fine. Thank you. Okay, find the output impedance of the difamp with cascode in place. Cascode. Okay. By the way, there is a fancy name for this. It's called telescopic cascode because it's long, looks like a telescope, right? So, okay. So that's the, some jargon. Fine. See you.